Welcome back to the Deep Dive. Today we're venturing into a realm that, for many, still feels like pure science fiction, directly interfacing with the human brain.
Yeah, it's definitely out there on the frontier.
Imagine a world where the most, debilitating neurological conditions, Parkinson's, epilepsy, paralysis, could be treated. Not with bulky external machines, but with tiny, really smart devices working silently inside you.
Or even restoring lost senses, maybe.
Exactly. Or even perhaps enhancing human capabilities, all with unprecedented precision and, crucially, safety. Okay, let's unpack this. Picture a future, right, where microscopic, totally untethered devices can not only precisely monitor your brain's incredibly complex signals, but also deliver gentle, really targeted stimulation,
All without wires.
all without wires, and without the need for repeated invasive secondary surgeries. Today, we're delving into some truly groundbreaking research from Purdue University that honestly propels us significantly closer to that reality.
It really does.
And this isn't just about making things smaller. It feels like a fundamental reimagining of how we can safely and effectively communicate with the brain.
Indeed. The specific source material we're digging into today is a very detailed research paper. The title's a bit of a mouthful.
Go on, let's hear it.
Okay, it's a 1.15 UWW 5.54 millimeter 3 implant with a bidirectional neural sensor and stimulator sock utilizing biphasic quasi-static brain communication.
Right, okay. Lots of jargon there.
A fair bit, yes. But at its core, it describes a specific technological breakthrough, a tiny system on chip and sauce that achieves really extraordinary levels of efficiency and, critically, safety for these neural implants. And that opens up entirely new avenues for how we interact with, well, the most complex organ in the body.
And our mission here, as always, is to navigate this exciting new landscape for you, the listener. We're going to break down how this incredibly tiny implant actually works, what makes its new communication method so revolutionary, and, well, why it represents such a huge leap forward for brain-machine interfaces.
Yeah, separating the hype from the actual achievement.
Exactly. Our goal is to leave you thoroughly informed, but, without getting totally lost in a sea of technical details. This deep dive is about understanding the impact and the implications of this amazing innovation. So let's set the stage first, because understanding the problem really highlights the genius of the solution, doesn't it?
Absolutely. Context is everything here.
Before we explore what's new, what have been the main challenges with traditional brain-machine interfaces? What makes this quest for truly untethered implants so absolutely critical?
That's the perfect starting point, because it really frames why this new research is so, well, profound. The fundamental issue with traditional BMX, the ones we've seen in, early applications and even some current clinical trials, is their inherent invasiveness.
Right, the wires.
Exactly. And the constant reliance on external connections. We're talking about devices that historically need wires, either directly poking through the skull or connected to larger components surgically implanted just beneath the skin. And those wires, those points of entry and connection, they introduce a whole host of really serious problems.
Like what specifically?
Well, think about it. Anytime you have a permanent pathway from outside the body directly into the brain environment, you significantly ramp up the risks. There's the danger of cortical scarring.
Scarring. Inside the brain.
Yeah, where the brain tissue develops dense, sort of fibrous material right around the implant itself. This can mess with the implant's long-term function, obviously, but it could also potentially affect the surrounding healthy brain cells.
Okay, it sounds bad.
It is. Then there's gliosis, which is another kind of tissue reaction, basically the brain trying to wall off the foreign object, and of course the constant, ever-present threat of infection.
Which has got to be a major concern with anything inside the brain.
Absolutely, a severe concern. Beyond that, there's even the risk of cerebrospinal fluid leakage, CSF leakage. That can lead to serious neurological complications.
Wow. Okay.
So when you add all that up, the scarring, the gliosis, the infection risk, the CSF leakage, the idea of using traditional tethered BMX for long periods for widespread use, it becomes almost prohibitively problematic.
It sounds like the solution itself creates a whole new set of dangers.
It really does. It's a solution that comes with such significant inherent risks that it just screams for a fundamentally different approach. We need something truly untethered, truly minimally invasive.
So if I'm hearing you right, it's not just about getting these devices to work in the short term. It's about making them safe and stable for years, maybe decades, inside a living brain. with minimal long-term harm.
Exactly. Viability and safety over the long haul.
And if physical wires are the main source of these problems, then researchers must have been pushing hard for untethered wireless solutions for quite some time, right?
Oh, absolutely. For years.
Yeah. What have they tried? And why haven't those attempts quite, hit the mark? It feels like there's always been some kind of hidden catch.
Precisely. The scientific community has definitely explored several wireless communication options, but each one came with its own significant trade-offs. The research paper we're looking at actually has a nice comparison figure showing this.
Okay, let's walk through those. What were the main contenders?
All right, so one of the first things they looked at was radio frequency, RF communication, similar to what your phone or Wi-Fi uses.
Seems logical.
It does on the surface.
Yeah.
But inside the human body, especially the brain, RF signals suffer badly from tissue absorption. Basically, the body soaks up a lot of the energy.
Meaning you need to transmit with more power?
A lot more power. To get the signal through effectively, you have to crank it up. Some previous studies mentioned in the paper used up to half a watt of power.
Half a watt. Is that a lot in this context?
It's huge. The paper points out that this exceeds the international safety guidelines, the IC&IRP limits, by roughly 10 times. 10 times. Wow. That's a massive safety issue, right? Especially for something permanently in your brain.
A non-starter for long-term use, pretty much. Even minor heating effects could be detrimental over time.
Okay, so RF had power and safety issues. What else did they try?
Then you have optical, OP, and ultrasonic US methods, using light or sound waves.
That sounds potentially safer. Less electromagnetic radiation.
In theory, yes, in terms of tissue interaction. But they come with a massive different problem. Extreme signal loss. Huge attenuation.
The signal just gets weaker very quickly.
Incredibly weak. The source paper gives an example for ultrasound, a staggering 110 decibel loss. That's mostly due to scattering and absorption by the skull itself.
110 dB, that's enormous. How do you even get a signal through that?
Well, to compensate, both optical and ultrasonic approaches often require something called a subcranial interrogator.
A subcranial? What now?
Interrogator. It's basically a secondary intermediate device that has to be surgically placed under the skull. Its job is to kind of boost or relay the signal. Wait, so you need another surgery just to make the wireless communication work?
Exactly. You're trying to avoid the invasiveness of wires, but you end up needing another invasive surgery anyway? It drastically reduces the overall efficiency and adds a whole new burden and risk for the patient.
That really does seem to defeat the purpose of going wireless.
It significantly undermines the benefit, yes. So safer in one way, perhaps, but it swaps one type of invasiveness for another.
Okay, any other approaches?
The third main category explored was magnetoelectric, or ME, methods. These tend to have low tissue absorption, which is good.
Sounds promising. What's the catch?
The catch is transduction loss. That's the inefficiency you get when converting energy from one form to another, like electrical signal to magnetic field, then back to electrical.
You lose energy in the conversion process.
You lose a lot. The paper quantifies this. To get the same energy density, these ME methods need a really large magnetic field, 0.1 millitesla. And that's equivalent to a massive electric field, something like 300 kilovolts per meter.
Whoa. That points to pretty severe inefficiency, right? Needing that much field strength.
Exactly. It indicates you're burning a lot of power just in the conversion process just to get a usable signal strength. So again, not ideal for a tiny, low-power implant.
So it really sounds like every single one of these alternatives had a fundamental, almost deal-breaking flaw. Dangerous power, needing another surgery, just being way too inefficient.
Pretty much. They all seem to trade one problem for another. It felt like a bit of an impasse.
But this is where it gets really interesting. Because this new Purdue research, the BPQBC thing, seems to tackle these core issues head-on without introducing those same kinds of trade-offs.
Absolutely. This is precisely the critical gap that this research aims to fill. They designed a fundamentally different communication method, this biphasic quasi-static brain communication, BPQBC, to directly address these limitations.
Okay, let's dive into that. BPQBC. Break it down for us.
Right. What's truly fascinating here, and really the core innovation, is this BPQBC. It's not just a small improvement. It's a completely different way of thinking about communication through the body tissue itself.
Okay. Biphasic quasi-static. Start with quasi-static. What does that mean here?
Quasi-static refers to using electrical fields directly for communication. It falls under the umbrella of body channel communication, or BCC.
Using the body itself as the communication wire, essentially.
Kind of, yeah. And the brilliance here is that it avoids the energy-wasting transduction losses we just talked about with optical, ultrasonic, and magneto-electric methods.
Because there's no conversion. It's just electrical signal all the way.
Exactly. No need to change into light or sound or magnetism and then back again. Each of those steps loses energy. BPQBC uses a direct electrical pathway through the tissue, much more efficient right off the bat.
Okay, that makes sense. Now, the biphasic part, what's the secret there?
This is where the really clever safety and efficiency engineering comes in. See, older forms of direct electrical communication, often called galvanic BCC or GBCC, had a big problem.
What was that?
The electrodes on the implant could essentially get shorted through the body's low-impedance tissue and fluids. This allowed a continuous DC current to flow.
Direct current, like from a battery.
Exactly, and that continuous DC flow is bad for two main reasons. First, it leads to really high DC power consumption, a huge drain for a tiny implant. Second, and maybe more critically, this DC current can actually disturb the delicate ion balance in the brain tissue.
Upsetting the brain's chemistry.
Potentially, yes,
Right.
which could lead to long-term damage or other adverse effects, something you absolutely have to avoid.
So how does BPQBC fix that, the biphasic bit?
It introduces a simple but critical component,
Mm.
a DC blocking capacitor right in the signal path. You can see it in the circuit diagrams in the paper.
A capacitor, like in basic electronics.
Yep. But here, it acts like a smart gatekeeper for the electrical signal. It allows the alternating current AC communication signals, the ones that oscillate back and forth, to pass through just fine. But it completely blocks any continuous one-way DC current from flowing into the brain tissue. This creates the biphasic output, a balanced signal that doesn't build up charge.
That's a powerful analogy. So it's like putting the smart filter on the signal. It lets the message through, the AC part, but stops the potentially harmful energy-wasting DC part, making it gentler and more efficient for the brain.
That's a perfect way to put it. You get the communication, but without the damaging side effects or the power drain of that constant DC flow. The seemingly small design choice, adding that capacitor, has huge implications. It's fundamental to the safety and efficiency.
Okay, so that explains the name. What are the main advantages that come out of using this BPQBC approach?
Well, they're pretty dramatic, actually. First and foremost, massive power reduction. Compared to traditional galvanic BCC at a typical frequency like 1 millihertz, BPQBC uses about 41 times less power.
41 times.
41 times. Think about your phone battery lasting 41 times longer. That's the kind of efficiency leap we're talking about here. Even at a higher frequency, 10 megahertz, it's still about 6 times more efficient.
That's huge for an implanted device that has to harvest its own power.
Absolutely critical. It means the device can be smaller, generate less heat, run longer on less energy. Second big advantage, very low channel loss. The signal doesn't weaken as much traveling through the tissue. The research shows less than 60 decibels of worst-case loss.
And is that good compared to others?
It's excellent. The paper states it's over 20 dBs better than prior art in this area. Less signal loss means more reliable communication over realistic distances, needing less power to transmit and receive.
Okay, lower power, less signal loss. What else?
Third, as we mentioned, no transduction losses. Because it's direct electrical, no energy is wasted converting the signal type. Pure electrical efficiency.
Got it.
Fourth, and this is a huge patient benefit, no need for those subcranial interrogators. Remember the extra surgery required for optical and ultrasonic?
Yeah, the booster device under the skull.
And BPQBC works directly between the implant and an external device, so one less invasive surgery. Less risk, less burden for the patient. It's truly untethered in the best sense.
That's a major advantage.
And finally, number 5, safety. The system operates using external electric currents that are less than 1/5 of the accepted international safety limits, ICN-IRP.
Much safer than those high-power RF methods, though.
Significantly safer. It ensures the communication itself isn't causing harm or unwanted side effects in the brain tissue, which is obviously paramount.
So lower power, better signal, no extra surgery, much safer. Sounds like a win across the board.
Yeah.
How does the whole system look? You mentioned an implant and an external part.
Right. The overall architecture involves 2 main pieces. At the core, you have the implant itself, the node. This thing is tiny. The paper gives the volume as 5.54 cubic millimeters.
How big is that really? Like visually?
Think of a grain of rice, maybe slightly thicker, but roughly that scale. It consumes, on average, an astonishing 1.15 microwatts of power.
Microdot watts. That's incredibly low.
It really is. The whole packaged implant weighs about 21 grams, still very light, and this node sits inside the brain. And it can do two things. It can sense neural activity and transmit that data out, and it can also deliver therapeutic electrical stimulation.
Sensing and stimulating. And it talks to.
It talks to the wearable headphone-shaped hub. This is the external part, designed to be worn comfortably on the skin or skull. Maybe like a sleek headband or, like minimalist headphones.
And what does the hub do?
It has two main jobs. It receives the neural data coming from the implant that's the uplink, or UL, and it also sends power and configuration commands to the implant that's the downlink, or DL.
Power and commands.
Yep. So you've got this tiny grain of rice device inside, wirelessly talking back and forth, and getting powered by this comfortable device worn on the outside.
Wow. Okay, so a grain-sized device in the brain talking to a headphone-like thing outside, using these gentle electrical signals. That just raises the question, how on earth do you pack all of that functionality, the sensing, the stimulating, the two-way communication, the power management, into something so incredibly small and make it run on practically no power?
It is a genuine feat of microengineering. The key is the highly integrated system-on-chip, or SoC, architecture.
System-on-chip, meaning everything's on one tiny piece of silicon.
Exactly. The entire brain of the operation is implemented on a single chip, made using a 65 nanometer CMOS process. That 65 millimeter refers to the tiny size of the transistors and wires on the chip, which is what allows for this extreme miniaturization and, crucially, the ultra-low power operation.
So what's actually on this SoC? What are the main building blocks?
All right, it integrates several core functions. First, there's the uplink UL transmitter, TX. That's the part that sends the sense brain data out to the external hub, the implant's voice, basically.
Got it, sending data out.
Second, there's the downlink DL receiver, RX. This lets the implant listen to the outside world. It receives the wireless power, but also vital configuration commands from the hub, tells it what to do, how to operate.
So it can be controlled from the outside.
Absolutely. Crucial for adjusting therapy or settings. Third, it includes the biphasic stimulator itself, designed specifically for delivering those safe, balanced electrical pulses for therapy.
The part that talks back to the brain.
Precisely. And fourth, essential for its untethered operation, is the RF rectifier, RR-based energy harvester. This is the circuit that captures a wireless power sent from the hub and converts it into electricity to run the whole implant.
No batteries needed.
No batteries, completely powered wirelessly from the outside hub.
Okay, but power is always the bottleneck for these tiny implanted things. Keeping something this complex running on microwatts seems almost impossible. How does this comm manage its energy budget so carefully? Are there some specific tricks they're using?
You're right. Power is the absolute constant challenge. And yes, this design uses some very clever strategies. One key technique is dual supply domains.
Dual supplies, meaning different parts run on different voltages?
Exactly. Parts of the chip that need to be always on, like the basic timer and controller managing the schedule but don't do heavy work, they run on an ultra-low 0.4 volts. Keeps their background power consumption minimal. But for the parts that need more oomph, like transmitting data or delivering a stimulation pulse, things that only happen intermittently, they switch to a higher 1-volt supply.
So just enough power for the job at hand, like shifting gears.
That's a great analogy. It optimizes power use across different tasks, but they go even further to fight leakage current.
Leakage? You mean power draining away even when parts are supposed to be off?
Exactly. It's a huge problem in tiny, advanced chips. To combat this, they integrated a tiny, very low-power 17 nanowatt charge pump, CP.
What does a charge pump do here?
It generates a slightly higher voltage, 1.8 V, called VPUMP. This voltage is used to bias the power gates, the switches that turn parts of the chip on and off when those parts are off.
And that helps reduce leakage.
Dramatically. The result is pretty incredible. It reduces the leakage current by 500 times. From about half a microwatt down to just 1 nanowatt.
500 times.
Ow.
That's huge.
It's like sealing a leaky faucet completely shut. It makes a massive difference to the average power consumption because the chip spends most of its time in these low power states. This is a key reason they can have that 1.15 microwatt average figure.
A 500-fold reduction in leakage. That's like turning off a dripping faucet and realizing you've saved half your water bill. It's a monumental energy saving. So what does this all mean for how the implant actually operates day to day or second to second?
Well, that extremely low leakage during inactive states ties directly into the overall operational strategy, which relies heavily on duty cycling.
Duty cycling, meaning it's not on all the time.
Exactly. It acts like a smart scheduler. By default, the system operates on a 1.1000 duty cycle.
1 to 1,000. What does that mean practically?
It means within a 100-second window, the implant might have a very short transmit phase, say 100 milliseconds, where it bursts out its data. Then maybe another short 100 millisecond stimulation phase. But for the vast majority of that 100 seconds, the other 99.8 seconds, it's basically in an ultra-low power sleep or listening state.
Mostly asleep, with short bursts of activity.
Precisely. And what's really neat is that this isn't fixed. The external hub can send commands down via the downlink to change the duty cycle, maybe to 1.10 or even 1.10 if more frequent sensing or stimulation is needed for a period.
So it's adaptable.
Very adaptable. And why is this duty cycling so important? Because it drastically cuts the average power use. By only drawing significant power in these short bursts, the energy harvested wirelessly from the hub has plenty of time during the long off periods to recharge the implant's internal storage capacitor.
Ah, so the long sleep times let the energy storage catch up.
Exactly. It allows the implant to run continuously on that minimal harvested power, balancing energy intake and expenditure really effectively.
This is where it gets really, really interesting for me. We're talking about collecting complex brain data, right? Signals that can be incredibly dense and information-rich.
Absolutely. Neural signals are notoriously complex.
But we need to send this data out using minimal power from a tiny device with very limited memory. How does this implant handle all that data? How does it avoid getting completely swamped, burning through its power budget, just trying to transmit raw signals?
You've hit on another major challenge, and this is where compressive sensing, or CS, plays a starring role. It's a core innovation here.
Compressive sensing. Okay, what is that in simple terms?
Well, traditional methods usually capture all the raw data first, store it, and then try to compress it before sending.
Like zipping a file after you've saved it.
Kind of, but for a device this constrained, that's often too late. You've already spent the power and memory acquiring and storing all that raw data.
So CS does it differently.
Yes. Compressive sensing is a technique that allows you to compress the data during the acquisition process itself. It's smarter about what data it captures in the first place.
How does that work? Like, how does it know what's important?
Imagine taking a photo. Instead of capturing every single pixel and then making the file smaller later, CS is like having a camera that intelligently figures out the most important parts of the scene as it captures the light and mainly records those, discarding redundant info from the start.
So it compresses on the fly.
Essentially, yes. The implant's SoC has what they call a wake-up-based CS front end. The technical details involve things like wavelet transforms and sensing matrices.
Okay, maybe skip the deepest math.
Right. But the key takeaway is that this system can intelligently identify and compress the important features of the neural signal right as it's being sensed. It figures out which parts are sparse, meaning they have only a few significant components, and focuses on those. It can even handle non-sparse signals effectively.
So it's like an intelligent editor, picking out the highlights in real time.
That's a good way to think about it. It throws away the less informative stuff before it ever consumes precious storage or transmission power.
And what's the impact? How much does it actually help?
The impact is huge. It drastically cuts the amount of data that needs storing and transmitting. The system offers a scalable compression factor, or CF, from 5 times all the way up to 33.33 times.
33 times compression.
Yep. And when it's running at that maximum compression, the power needed for a 10 millipiece transmission burst drops from over 7 milliwatts down to just 217 microwatts. Even accounting for the CS processing itself, that's about a 16-fold reduction in overall transmission power.
16 times less power just from being smarter about the data.
Exactly. And it also slashes memory needs by more than 10 times compared to just storing everything first. The paper shows examples of reconstructing EEG signals accurately even after this level of compression.
So it's not just sending data, it's intelligently filtering and compressing it right at the source, saving massive amounts of power and storage. That is a huge efficiency gain for something so small. It's like having that hyper-efficient assistant sorting your information before it even hits your inbox.
It absolutely is a really elegant solution to a major bottleneck. And speaking of elegant solutions, think about the future. Maybe you have not just one, but dozens or hundreds of these tiny implants working together in the brain.
Wow, okay. A whole network of them.
Right. But then you immediately hit another problem.
Right.
How do they all talk without constantly interfering with each other? It's like having a room full of people trying to shout at once. You need some kind of traffic control.
How do you manage that in such tiny, low-power devices. You can't run complex network protocols on them, surely.
Exactly. Traditional network management like MAC, layers, and Wi-Fi are way too complex and power-hungry for the scale, so they needed another clever, low-power solution.
They found one.
They did. It's called ROPUF-based collision avoidance.
ROPUF. What does that stand for?
Ring oscillator, physical unclonable function.
Okay, that sounds complicated.
The concept is actually quite neat. A PUF, or physical unclonable function, basically uses tiny, unavoidable manufacturing variations that exist in every single silicon chip. These variations are random and unique to each chip, like a fingerprint.
So every chip is slightly different, physically.
Minutely, yes. And the ROPUF uses these differences specifically in the timing of simple circuits called ring oscillators to generate a unique, random digital fingerprint for that specific implant chip. It's unclonable because you can't predict or copy these manufacturing variations perfectly.
Okay, so each chip has a unique ID based on its physical imperfections. How does that help avoid collisions?
This unique PUF output is combined with a standard pseudo-random sequence generator in 9-bit PRBS. The result is that each individual implant node gets assigned unique, staggered time slots in which it's allowed to transmit or stimulate.
So based on its unique fingerprint, it gets its own specific turn to talk.
Precisely. It ensures that, statistically, it's highly unlikely that two nodes will try to transmit or stimulate at the exact same moment. It provides collision avoidance without needing any complex negotiation or central controller.
That's incredibly clever. Autonomous traffic management built right into the hardware.
It is. It dramatically simplifies the system, saves power, and makes a network of these devices inherently more robust. Each chip just follows its own unique, physically determined schedule.
Astonishing. So it's like each implant gets its own unique randomized time slot, preventing them from shouting over each other based on its own physical nature. That addresses a future with many implants beautifully.
It really does. It's thinking ahead. And of course, all this amazing activity, the sensing, the compressing, the communicating, the stimulating, the collision avoidance, it all needs power.
Right. Back to power. You said no batteries, powered wirelessly. How exactly does that energy harvesting work?
The implant gets its power via energy harvesting using that RF rectifier circuit we mentioned earlier. Specifically, it's a highly efficient 30-stage RF rectifier.
Okay, and what does the rectifier do?
Its job is to capture the energy being beamed wirelessly from the external hub, which is sent using those same quasi-static electrical signals, and convert that incoming energy into a stable DC voltage to power the chip.
How sensitive is it? Does the hub need to blast it with power?
No, that's the beauty of the efficient BPQBC communication. The rectifier is designed to work very well even with low input signals. It can generate the needed 1-volt supply from an input signal of only about 70 millivolts peak to peak coming from the hub.
So the hub doesn't need to transmit huge amounts of power either.
Correct. It keeps the whole system efficient and safe. The harvested energy is then stored temporarily on the implant in an external storage capacitor, C-store, usually around 40 microfarads.
It's a tiny energy buffer.
Exactly. And this capacitor is carefully chosen and managed. It's designed to charge up quickly in less than 100 seconds from empty. And crucially, it's designed so its voltage doesn't drop too much, less than 100 millivolts, even when the implant does its power-hungry transmitting or stimulating bursts.
So it provides a stable power source even during peak activity.
Precisely. It ensures the implant has the juice it needs, when it needs it, making it truly self-sustaining from the wirelessly harvested energy.
So the wearable hub isn't just listening and talking, it's constantly trickling power to the implant too. That completes the picture. A fully self-contained ecosystem.
It really is. Sensing, stimulating, communicating both ways, intelligently managing data, and powering itself wirelessly, all in that tiny package.
Okay, let's talk performance then. We've heard about the low power, but how well does it actually communicate? Let's start with sending data out, the uplink performance.
Right, the UL, from the implant node to the external hub. The numbers here are really impressive, especially on energy efficiency. With compressive sensing turned on, running at that top data rate of 10 megabits per second, it achieves an efficiency of 52 picojoules per bit.
Picojoules per bit. Is that good? How does it compare?
It's outstanding. The paper states this is a more than 60 times improvement in energy efficiency compared to previous state-of-the-art narrowband BMX.
60 times more efficient at sending data.
Yeah, imagine a car getting 60 times the mileage. That's the scale of improvement in how little energy it uses to transmit each bit of brain data.
Incredible. And the data rate itself?
It's scalable. It can go from 6 kilobits per second up to that 10 megabits per second maximum. Very flexible.
And the power consumption during that transmission.
The active power, just for the transmission part, is only 0.52 microwatts at 10 MeV, excluding leakage. When you factor in the average power, including leakage and the CS processing, you get back to that overall figure of 1.15 microwatts.
Which, crucially, is low enough to be sustained by the harvested power.
Exactly. It lives within its energy budget. And compared to other narrowband implants, this system achieves by far the highest data rate, something like a 3,000 times improvement over some examples cited. It's just operating on a whole different level.
Okay, that's sending data out.
Yeah.
What about receiving commands and power? The downlink performance.
The DL, from the hub to the node. This side is also incredibly efficient, as it needs to be always listening, essentially. The receiver circuitry runs on just 31 nanowatts.
Nanowatts?
Yeah.
Even less than the average.
Much less. Its energy efficiency for receiving data is less than 35 picojoules per bit at a typical downlink speed of 1 kilobit per second. This ultra-low power reception is vital for reliably getting those configuration commands and control signals from the hub without draining the harvested energy.
So both sending and receiving are hyper-efficient. What about the stimulation part? Can it actually deliver meaningful therapy?
Yes, the stimulation capabilities are well integrated and configurable. The biphasic stimulator itself is highly efficient, about 89.2% efficiency in converting input current to stimulation current.
Meaning not much energy is wasted in the stimulation circuit itself.
Correct. It can deliver a maximum stimulation power of 1.2 milliwatts and a maximum current of 1 milliampere, which is significant for therapeutic applications.
Can you control the stimulation pulses?
Very precisely. The external hub can set the pulse widths, the duration of each pulse, anywhere from 32 microseconds up to about 4 milliseconds, 48 and 96 cents, in 8 steps. And it can also set the time interval between pulses, from 1 millisecond up to 128 milliseconds, again in 8 steps.
So you can really fine-tune the therapy pattern.
Absolutely. That level of granular control is essential for tailoring the stimulation to specific conditions, patients, or research goals.
Okay, the design sounds incredible, the specs are amazing, but it's one thing to simulate this or test it on a workbench. Did they actually prove it works in conditions that resemble a real brain? How did they test the BP-QBC channel itself?
That's the crucial validation step, right? And yes, they performed rigorous channel measurements to confirm the concept works in a biologically relevant environment. They set up an in vitro test specifically to measure the BP-QBC signal transmission.
In vitro, so using biological samples.
Yes. They used thin slices of mouse brain tissue, kept alive in artificial cerebrospinal fluid, CSF. These slices were between 0.5 millimeter and 2 millimeters thick. They also ran tests using a saline solution, PBS, in a container specifically sized to mimic the dimensions of a human skull, about 110 millimeters across. They place electrodes either on the brain slices or in the saline solution at realistic distances.
And measured how much signal got through.
Exactly. They measured the channel transfer function, basically the signal loss.
And what did they find? Did BP-QBC work?
It worked very well. In the mouse brain slices over a 10 millimeter distance, the channel loss was only about 20 decibels, which is quite low. In the larger human skull-sized saline setup, simulating longer distances like 55-60 millimeters, the loss was higher, around 60 decibels. But crucially, this was still well within a manageable range for the system's sensitivity and power.
So the measurements confirmed their models and showed as feasible in brain-like conditions.
Precisely. It validated their analytical predictions and, importantly, demonstrated the real-world feasibility of BP-QBC. Because the implant design is so small, this work actually represents the first time anyone has made realistic BCC-based channel measurements for such a tiny implant within a biological context. It moves it from theory to demonstrated function.
It's a huge step. Proof of concept in a relevant environment.
Absolutely critical. So if we step back and look at the whole picture, what this Purdue research represents is really a collection of significant breakthroughs all rolled into one tiny, cohesive system.
Let's summarize those key achievements.
Okay. First, it's the first demonstration of body channel communication being used for an implant that is genuinely grain-sized under 6 cubic millimeters. That miniaturization itself is a massive step for reducing invasiveness.
Right. Tiny size matters.
Second, and technologically the biggest leap, it's the first implementation of biphasic quasi-static brain communication, BP-QBC. This specific method is the key enabler for the huge power savings and the enhanced safety due to eliminating DC currents. It's fundamentally better than older galvanic BCC.
the core communication innovation.
Third, the integration of compressive sensing, CS, directly on the chip for intelligent data reduction. That's a really smart way to handle complex neural data within extreme power and memory limits.
Built-in data smarts.
Fourth, use of ROPOF-based collision avoidance. This provides an elegant, low-power way to allow multiple implants to coexist and communicate without interference, paving the way for future network systems.
Future-proofing for multi-implant scenarios.
And finally, the crucial point is the integration of all these things simultaneously. Wireless powering, two-way data communication, uplink, downlink, the compressive sensing, and the therapeutic stimulation, all happening in a single, ultra-miniaturized, completely untethered implant. That comprehensive integration, combined with the unprecedented efficiency and safety in such a tiny form factor, it really marks a new benchmark, potentially a new era for neural interface technology.
That's genuinely astounding. So if I'm wrapping my head around this correctly, we've gone from these clunky, risky wired implants through various flawed wireless attempts to something the size of a grain of rice.
Yeah.
And this tiny thing can listen to the brain, talk back to it via stimulation, communicate both ways with the outside world, power itself wirelessly, and intelligently manage its own data to save energy, all without a single wire piercing the skull.
That's the achievement in a nutshell.
That is a complete paradigm shift for neural interfaces. It's just a remarkable piece of engineering. Wow, what an incredible deep dive.
We started by looking at those really significant, sometimes dangerous challenges of traditional brain-machine interfaces.
The wires, the infections, the scarring.
Yeah.
Exactly. All those risks with tethered devices. And then the drawbacks of the earlier wireless attempts, the RF power issues, the optical and ultrasonic signal losses, needing that extra subcranial surgery.
Yeah, none were quite the magic bullet.
Then we journeyed right into the heart of this Purdue breakthrough, this biphasic quasi-static brain communication. We unpacked how quasi-static avoids those energy-wasting conversions.
Direct electrical path.
And how the biphasic trick, using that simple DC blocking capacitor, is the key to slashing power use and making it so much safer by getting rid of harmful DC currents.
Fundamental improvements there.
And we can't forget those brilliant on-chip solutions. The dual power domains, that incredible 500x leakage reduction, compressive sensing, doing smart data compression on the fly.
And the ROPUF collision avoidance, letting future networks of these things play nicely together. It's a whole package of innovations. And if we connect this to the bigger picture, thinking about the impact, this kind of technology really does pave the way for a whole new generation of neural interfaces.
What kind of applications are we talking about?
Well, imagine the potential for treating a much wider range of neurological disorders. Things like Parkinson's tremors, epileptic seizures, maybe even helping recovery after spinal cord injuries or stroke. Devices that could be far more effective, but also much safer and less invasive for patients long term.
And beyond treating disorders.
You could think about restoring sensory functions, maybe new possibilities for people with profound blindness or deafness. And then further out, perhaps, you get into the realm of augmenting human capabilities. But the immediate promise is really about creating these highly integrated, practical, long-term solutions that can blend almost seamlessly with our biology, significantly improving quality of life for people with serious conditions. It's moving beyond bulky, risky implants to something far more elegant and viable.
This deep dive has definitely shown us how incredibly clever engineering, really driven by a deep understanding of the biology and the physics, can overcome challenges that seemed almost insurmountable just a few years ago, transforming clumsy and dangerous into something elegant, safe, and incredibly efficient.
It's inspiring stuff.
It really is. So what does this all mean for you listening right now? Consider this. If we can now make devices this tiny, this efficient, to communicate within the complex environment of the human brain.
Empower them wirelessly through our own body tissue.
With this level of precision and safety, what other kinds of impossible-sounding, deeply integrated human technology interfaces might be just around the corner? Maybe powered by equally innovative, body-friendly communication methods we haven't even dreamed up yet? The boundaries of what we thought was possible in human-machine integration are clearly and very excitingly shifting.